Hello, and welcome to our Schulich Connects on nanotechnologies. I would like to take this opportunity to acknowledge that the University of Calgary is on the traditional territories of the people of the Treaty 7 region in southern Alberta, and the city of Calgary is also home to Métis Nation of Alberta, Region 3. A few housekeeping items before we get going. We will be using Zoom's Q&A function. And so if you look at the bottom of your screen, you'll see the Q&A, and feel free to post questions at any point during the seminar. And as we go through, I will be asking some questions, but I will also start to ask our panelists your questions. We're very excited today to have a very thorough conversation about nanotechnology, what's being done in Canada, and how that's having an impact today and into the future. Before we get started, I have a few pieces of great news to share with you. For those that attend our Schulich Connects regularly, you've heard me talk before about our Bioengineering Summer Institute. This is a unique program where we can admit students into engineering using biology, grade 12 biology, as opposed to their grade 12 physics. And what we do in this program is we start with biological concepts. We introduce biomedical engineering. And from there, we introduce the students to all the material they need to know from high school physics so that they can be successful as an engineer. The good news is that late last year, we were informed that we are recognized with the Learning Resources Network Award for Excellence in Program Development. And this program is just another example of how we're creating additional pathways for students who might not initially think about an engineering career to actually go into engineering and really thrive. Another piece of really exciting news is that we're going to have a department name change in just over a week. Our Department of Electrical and Computer Engineering will be renamed the Department of Electrical and Software Engineering starting in March 1st. The reason for this is we've seen tremendous growth in our software engineering activities at both the undergraduate and the graduate level, where we have now more than 200 students a year joining our undergraduate program, making it one of the largest programs in Western Canada and at the Schulich School of Engineering. Speaking of Western Canada, a few weeks ago was the Western Engineering Competition. And I'm really happy to announce that two Schulich software engineering teams took first and second place in their category in the Western Engineering Competition. And they will be joined by 4 other teams. So 6 teams in total from the Schulich School of Engineering will be competing at the Canadian Engineering Competition this coming weekend. We'll watch their progress with interest, and I'll be happy to report at our next Schulich Connects how they've done. Now on to nanotechnologies. Let me introduce our esteemed panel for today. Here to talk about the unseen world of nanotechnologies and how they make a difference in our lives. First, it's my pleasure to introduce Dr. Marie Doriot, who is the president of Nano Canada and also works with the University of Ottawa as the director of Nexus for its Quantum Technologies Institute. Maria, welcome. Next, we have our very own Dr. Milana Triskovic, who is an associate professor in the Schulich School of Engineering's Department of Chemical and Petroleum Engineering, and also very involved in the local startup community with a startup called Invicor. And next we have Dr. Colin Dalton, who's an assistant professor with the Schulich's newly renamed Department of Electrical and Software Engineering. He's the director of our Microsystems Hub, and he's the co-founder and the chief technology officer of UCalgary startup Neora. So panelists, welcome to you all, and thank you very much for being here. To get things started, I wonder if each of you could tell us what role you are currently playing in advancing nanotechnologies in Calgary, Canada, and around the globe. Marie, would we like to start with you?
Sure, thank you very much.
Thank you.
Well, Nano Canada is an industry association. Of course, it's not just for industry, it's also for academia and government stakeholders. But what we do is basically link the community in advanced materials and nanotechnology across Canada, but also internationally. And I've been its founder and president since 2015. So what we do, in fact, is we organize events like webinars and national conferences, and our first international conference that's coming up virtually in October and in person, I hope, in 2022. So that's what I'm doing in terms of nanotechnology. That's my role, my direct role for nanotechnology.
Milana, do you want to follow?
Sure, thank you. So I can tell you first maybe what my group focuses on. So in general, we're passionate about design of advanced materials for energy sector. And by energy sector, I really mean a very wide scope of applications. So we would be developing materials for energy conversion and storage devices, but we could be also developing nanosensors to monitor these electrochemical reactions. But at the same time, we could be also going and developing nanosensors for monitoring fracking, for example, process. And at the same time, we could be also developing technologies for mitigating tailing systems in oil sands and hard rock sector. So as you can see, like the application spectrum is really, really wide. But we're really, where we play the role is actually going and understanding, providing understanding to how the building components of materials really interact at this small scale, and how they govern what we see in the large scale, and how can we tailor them to achieve these key performing indices. So as such, as I mentioned, from these vast number of applications, there are applications that are really close to home, like oil sands, but there is also something that we're looking into, how can we contribute to the global problems, like, how can we actually go and switch more to the renewable sector.
And Colin, what about you?
Thanks, Will. So I'm working on, not on nanoparticles exactly, I'm working on the nano engineering side of making like microelectrodes and microsystems and integrating nano to that. So I work in the biomedical engineering field. So I work with implantable medical devices and lab-on-a-chip devices for faster diagnostics of things like COVID and stuff like that. I'm running the clean room facility at the U of C. So that's a microfabrication facility that enables researchers and local businesses in Calgary to kind of make things in the micro nano scale. I'm also working with Marie on the conference that she mentioned. I'm also working with the SPIE, the International Society of Photonics, on their large conference that happens usually every year in San Francisco, but will be online this year. It's on microfluidics, biomems, and medical microsystems. Obviously, I've got a spin-out company, which is related to some of the research that I've been doing with colleagues in the Cummings School of Medicine on brain-machine interfaces. And I also, as with Maria, we teaching, and Milana, we teach in the micro-nano space. But I also do a lot of kind of reach out work and mentoring on the side for anybody who's interested in doing startups and entrepreneurial and how to spin up research as well, to try and help people navigate into the real world from the academic world.
It's all very exciting. And before we dive deep into some of those applications and how they're really making a difference, why don't we take a step back and get you to help define to those that have joined us here today, what exactly are nanotechnologies? And for those that haven't heard about them as much, why haven't we? Marie, you're with Nano Canada, so I would think there's a perfect place to start, and then we'll let one of our other panelists jump in there.
Sure. So the definition of nanotechnology is whatever it is with materials, for example, where in one of the dimensions the scale is a billionth of a meter, 10 to the minus 9 meters. So that's extremely small. So if you think of a sheet of paper, that's 100,000 nanometers. So it's extremely small. And in order to work at that scale, of course, we've needed to develop a lot of tools to manipulate and image these things. And you know, we might not have heard about it. It's actually been a field that's been recognized for the last 20 years, but it actually predates that. And maybe I'll let the others talk a little bit about the history of it.
I can go next.
Yeah, that'd be great.
Yeah, I think like, you know, my favorite definition of nanotech, and I think like I heard it somewhere at the conference, is actually making small stuff do big things, but at the same time try to sell them. And I think like, you know, maybe instead of saying like trying to sell them, I think what we're trying to do is like solve these do big things and implement them at large scale, right? And as Marie already mentioned, it goes back and back, hand in hand to development of electron microscopy, where we could really now probe and understand what we're working with. But if you go back in the history, we've been using gold colloidal systems where people figured that, for example, gold in bulk will have a different color. We know how it is if you have gold jewelry, but actually if you're decreasing the size, it becomes very red, right? So now like that optical change in gold as you change its size has been used in stained glass forever, right? So we've been using it. It's just now that we actually have a term nanoparticle and we know and we can characterize that nanoparticle, it really enabled now, you know, in some sense, like even marketing nanotechnology, and also now that it's entered really commercialization stage, now like I think like, you know, that definition becomes, or understanding becomes a little bit more clear.
Colin, do you want to add to that?
Sure, I'd like to build on it from the microelectronics side of things, because you know we're all watching this this webinar on laptops and tablets and potentially even our phones, and the reason for all that miniaturization is that we've been able to miniaturize the size of transistors, and they are currently at what is known as the 5 nanometer node. So all of our technologies from the last 30 odd years have been based on nanotechnology. And the actual fundamental way that we create a transistor is by controlling the doping of the material, the silicon chips that we hear about. And that's by actually putting in individual or very small amounts of other elements to change their electrical properties. So we have been using nanotechnology for decades, but it's only more kind of recent that it's become common in the media, I would say.
I think too, if for those of us who wear makeup, nanotechnology is in most of our creams and so on. And, you know, if we haven't heard of nanotechnology before, we're in the COVID era, and probably the largest, the product that is influencing all of us is some of the vaccines that people call, you know, messenger RNA. Well, it uses nanotechnology to deliver the RNA to the cells, and they've proven to be very effective from what we know, very effective vaccines when we get it in Canada. But you know, that's probably the nanotechnology application that's affecting all of our lives right now. So that's very exciting.
Well, actually, I can build on that because obviously the technology to analyze all the data that's coming from these clinical trials and all the processing power required to understand what's happening with the messenger RNA comes from having all these bigger, faster, better computers, which have been enabled by having nanotechnology systems and reducing the size and making the speed better and all that sort of stuff. Sorry, Bill.
Mm-hmm. Yeah.
No, this is great, Colin, and I really like the fact that you're having a debate on the value of the nanoparticles versus the microelectronics. So it's going to be a good entertainment to see this duel go on for the rest of the panel here. And so Marie, you brought up COVID, And maybe with that, could you explain what are we actually doing? Like, how are we using nanotechnology with respect to the vaccines, with respect to work that's being done to combat COVID-19?
Mhm. Well, there have been a lot of applications developed in the last year. I mean, just to think about coatings, for example, a lot of companies have pivoted to take their product and develop coatings that are antiviral. So, you know, if you go on the subway, for example, some of the surfaces are sprayed with coatings that repel the virus. So inks as well for various textiles too have been developed. For the vaccine, it's really what is working very well with these lipid nanoparticles is that they envelop the nucleic acid and they go into cells very efficiently, and it's more efficient than the other ways that have been used before. And that's really the breakthrough. And the fantastic thing is this is a Canadian breakthrough. It's our Canadian nanomedicine community that's developed that. And Colin was talking about microelectronics. Well, in Alberta, there's been Alberta was a pioneer in development of microfluidics and lab on a chip. That is a technology that is a revolution now for pharma, because you can use very little material to test different drugs, and it's all miniaturized and reconfigurable. And that's a manufacturing revolution that's just starting, and Canada is a front player in that. So it's tremendously exciting, and it's taken a long time to get there because it's complicated. But we're finally there seeing applications in the real world, and I think it's great. So I could go through lots of different applications for COVID, but the main ones that I can think of are really linked to coatings and things to repel the virus.
I would build on what Marie has said in terms of, I know there are many researchers in the biomedical engineering program here at the University of Calgary that have stepped up into the lab on a chip side for the diagnostics for COVID. Milana herself, I believe, did a great job, and I'll let her talk about that. I won't steal your thunder, Milana, when to do with something related with COVID. And yeah, Alberta hosted the first conference called MicroTAS, Total Analytical Systems, which was the name for lab on a chip way back when, and the first conference was in Banff, and I remember hearing about it when I was doing my microfluidics work back in the UK. So Alberta is on the map in that respect, and we've been developing lots of things in the different universities to help actually detect this. There's also been a lot of research looking at the AI component of COVID diagnosis and stuff, and again, that's all enabled by having faster computers, understanding neural networks, and all that sort of side of the research, which is also something that's very strong here. I'll let Milana go with her story.
Yeah, Milana?
Yeah, just to add to that, as Mary said, a lot of companies that were working in coding essentially use their knowledge and kind of apply it to the COVID situation. And I find that happened a lot in the research world in general with the scientists as well. And then we, as Colin said, we had basically an army of Schulich faculty that tried to essentially use their knowledge, their base, to contribute. And I think, so if you think about so another obvious example of where we can use, where we see nanotechnology taking place is actually face masks. So N95 were a really, really great mask. It is not recyclable, so therefore it's not sustainable mask, right? So then there were huge effort invested into how can we actually make reusable masks, and what are the building blocks if you want to make a reusable mask is going to be some sort of a nanoparticle that is sustainable in nature. It will be connected to conductive nanoparticles, usually two-dimensional nanoparticles, so we can actually recharge by just passing low current, essentially remove old viruses, but at the same time reuse it, right? So that is the idea that a lot of people actually around the world have started tapping into. But then also, if you look at these rapid diagnostic tests, right? So a lot of these tests were developed before. So lateral flow assays were developed to detect other viruses. So then in parallel, what we have and what we see is a lot of this development on the point of care diagnostics. And if you look at really the basis of it, it's still going to be some sort of a nanoparticle. A lot of them will have the same gold nanoparticles, what we use for centuries, because they happen to be really amazing, as I said, not only for the optical properties, but we can functionalize them. We can change their surface very easily so they can bind to the virus. As they now change, if they bind to whatever we're trying to detect, whatever molecule it is, then they will either change, make a shift in their optical properties or in their aggregation state, which is really important. And that's how you can actually get like, okay, it's a positive versus negative test. And so these two examples are just, for example, like, you know, so I've never worked in biomedical space before, but when COVID-19 happened, then we understood that we have tools to actually contribute to this field. So then we teamed up with the people that are experts in these applications, and we could actually contribute in this space. So I think, like, you know, as Colin said, we're one of many, many groups that have done the same in Schulich, in mechanical engineering, in electrical engineering, chemical engineering, and biomedical, of course, as well.
In your opening comments, you know, we've heard nanoparticles described as take a piece of paper, you know, very thin, and there's 100,000 nanoparticles in the width of the paper. And Milana, you said, you know, small particle, big impact. How can something so small, I can imagine some of those that have joined us today, imagine this little tiny particle. How can something so small be having the big impacts that you're talking about here today?
I can go first if you want me to.
Always good to start with the chemical engineer.
Thank you. Yeah, I believe so too. No, I'm just kidding. So if you think about all the, I'm going to start with stuff that we heard about in the news, right? So we heard about graphene at some point, two-dimensional wondrous nanoparticle, right? Like, so if it, and it's still the form of carbon. So like, you know, graphite being in your pencil lead, very soft, diamond being super hard. And then you go, as you decrease the size and you get to this two-dimensional sheet of graphene, of carbon atoms that are kind of like a chicken wire, but these carbons are really, really tightly bonded. You get like these remarkable properties. You get the lightest, the toughest, and superconducting material. So then, you know, so that was a big, big hope for the scientific community for the, okay, graphene will do wonders. Now, graphene on its own, it took a while for us to figure how to essentially produce it at scale. We can produce it at scale. But then at the same time, we also understood that we have to in parallel figure how to structure this wondrous material so we actually keep all of those nanoscopic values. Because what happened at the very beginning, we would have like this amazing nanoparticle, and then you throw it, for example, in polymer matrix to make conductive polymer nanocomposites that will have like a lot of different applications. Well, what you see is that the same wondrous material is actually very incompatible with many other components. So you actually now have, well, you lost your nanoscopic value because you actually get marginal improvements in comparison to your conventional additives. So really in hand and in parallel, what we have done, we were also understanding how can we actually assemble these nanoparticles. So you go back to those building blocks. You go back to the interactions with themselves, interactions with the other components of either the material that you're developing, or if you're actually looking at developing, injecting them in a certain process, then you have to also understand in what environment will they actually be? How can you tune those properties so that you really capitalize on these great properties that they have when you look at the single nanoparticle? So I think, like, you know, how can they do it? It's because, again, by size, you're actually getting these amazing properties when you go to this super small level. But at the same time, you have increased surface area, obviously, like, I mean, beside those things. But at the same time, you have to understand how to structure these things properly so that they do what they really are able to do and capitalize on them in the best possible way.
I think, oh, sorry.
Oh,
I think
sorry.
the other thing is that what's different about nanotechnology is that, you know, we take what we have always known as materials, and suddenly as we make them smaller and smaller, we have more surface area, and that changes the physical chemical properties of the materials, and they have different properties if they're 100 nanometers versus 50 nanometers. And that's a complexity I was alluding to, is that depending on the size, your properties are quite different. Milena talked about gold nanoparticles, different colors depending on the size, but they act differently. And so, it's been a process of discovery. Even if you take wood, okay, piece of wood, you can turn that into, and it was surprising, a nanocrystalline cellulose. So the cellulose actually at the nanometer scale is crystalline, or it can be a fiber as well. But suddenly it's not like our regular wood. It's extremely strong. It's biodegradable. It's not active. It's great for health applications. So suddenly we're faced with this series of different materials that we hadn't expected, and we can go and study new properties, new applications. So it's really a very rich playground, if you will, but with that, of course, comes some of the complexity in understanding why is it like this at this scale and not at that scale. So there's a lot of physics and chemistry and engineering and materials engineering that goes into all of that. But it's really exciting because there is suddenly that new sandbox for materials.
Yeah, and I'll add to that.
Go ahead, Colin.
I think it was Milano mentioned earlier about the advent of the scanning electron microscope in the 1960s and so, that allowed us to see into this, the nano realm. And by being able to see what was happening, we could then start to manipulate it to understand why things were behaving as they did. So a lot of nanoparticles and bits and pieces are in things like paint. And they were looked at things like the lotus leaf in nature as to why was it why did it repel water? And they realized it had a very, very interesting nano structure. And then we basically have mimicked that. So that when some paints dry, they will form that surface feature in the nano scale, and then that will enable the paint to basically last longer because dirt and water will come off it. And then if you go back to kind of the electronic engineering side of things, why does something so small actually change or have such an impact? The whole silicon industry is based on having a very, very pure material, silicon, and then introducing individual atoms to change its properties to what is known as semiconducting, and then changing those to be what is known as P-type or N-type, which means that they have different ways to conduct. And then this is how we build up our transistors. And the original first transistor was massive. It was almost like two massive pieces of material. And now they're in this 5 nanometer realm, and we can actually structure the whole thing to controllably structure it in all 3 dimensions. And that's what's giving us all our computers and things. But by just introducing those original materials together, change the properties. And that's also what's happening, which something that Marie alluded to, is we have the structures. We have materials that we are very familiar with, like plastics and things like concrete. But if you add carbon nanotubes to them, only maybe about 1% of the mix, you totally change their structures. You can change them from plastic to be conductive. And this is some of the research that's been done in CPE and mechanical here. And also You can change them to be maybe a better insulator for electromagnetic shielding for our mobile phones, so they become lighter. You can make self-healing concrete, improve the structures of roads. Everything starts to change.
Well, this is all very exciting, and sometimes I'm sure it seems to some of our audience members like we're in a sci-fi movie when you're talking about some of the work that you're doing with nanomaterials and nanotechnologies. Marie, I introduced you as being the lead for Nano Canada. Can you tell us a little bit about Nano Canada?
Sure. Well, back in 2015, I was leading the National Institute for Nanotechnology in Edmonton. And I came to realize that, you know, in Canada, we were a lot of solitudes. When we went to international conferences, there was Alberta, there was Ontario, Quebec, but everyone spoke about what was being done in their province, but we had no presentation for Canada as a whole. And I knew how rich, you know, the landscape was in terms of what was being done in Canada. And so I got a few people together and said, well, how can we change that? And what I heard, it was interesting. The industry was saying, you know, we want to work with researchers, and we feel that there's a window of opportunity. We must work together and commercialize some of the discoveries. We want products on the market. We want to be competitive on the international market. What can you do to help? And so that's why we launched Nano Canada in 2015. At that time, it was as part of the National Research Council. And then I incorporated as a not-for-profit in 2018, once I was away from the National Research Council. And what we've developed there is a way to connect people, making introductions between industry and researchers and academia, but also, you know, we organize trade delegations to various countries, and we bring a Canadian delegation, and they get to talk to other companies or other researchers in these countries. And there are research contracts that come out of that, sales, distribution networks. There's a lot of impact from being able to present yourself on the international market and talk to others. But there's a lot of learning between ourselves, like one Canadian company talking to another Canadian company saying, oh, you're doing that, I could help you. You know, have you tried this or that? And it's that, in a sense, an ecosystem. It's bringing all the players together, and we can do so much more when we're together than when we're apart. And so what we've been trying to do is basically say, what's missing? Is there a role that we could play? Is there a gap? And so we're now involved with ISO's, the standards for nanotechnology. So we provide leadership to the Canadian working groups. We also have convened the Health and Safety Committee. So people from government, from academia, from industry, we talk about, you know, what are the problems with health and safety, with nanotechnologies, what do we need to know, you know, where are the resources to inform those who work with these. And so we're having our first webinars this year. So we're trying to fill some gaps. And this year it's been about nanomedicine. When we saw what was happening with COVID and the vaccine, we thought, you know, that this nanomedicine community is very close to our advanced materials and nanotechnology in engineering and faculties of science. Why not bring all of that together? And so that's what we're working on now, is building that nanomedicine ecosystem across Canada. So that's really what's driving us in a sense.
It's exactly what we need in so many more areas as well. We've heard a lot of really exciting applications that are happening here in Canada using nanoparticles and nanotechnologies. And I'm just wondering if the three of you could take a moment to speak to our audience on what are Canada's strength areas when it comes to nanotechnologies now, and where do you see the strength areas in the next 3 to 5 years?
I can start maybe.
That would be great, Milana. Thank you.
So, I mean, Marie mentioned cellulose nanocrystals before. I really think, like, you know, if you look at Canada in general, I think like we always have our strength is in our resources always, and it's no different than in nanotech space as well. So, if I think about Canada, well, we have like, you know, a huge forestry sector, and there was a strategic mandate to actually do something about that. So as a result, we have Cellulose. We have one of actually the world's largest cellulose nanocrystal plant in Ontario, for example. So that's something that we should really be proud of. And when it comes to the cellulose nanocrystal, so Marie talked about it a bit, but it's a really, I think like we're just tapping into its potential. So it's not only in the biomed space, it behaves as a liquid crystal as well. And, you know, there is these really cool applications where people actually kind of think that they can make, or there's research ongoing to make, for example, windows from cellulose nanocrystals because of their optical properties. And that's just one. But then also, if you think about that sustainable aspect of them, easy functionalization of them, that is all something that you really want out of the nanoparticle, because that means that it's easy to compatibilize it with other components to make these advanced materials. I think if we look at Alberta, so if you, I think like if you look at the challenges by Alberta Innovates, and the recent one was transforming asphaltenes into carbon fibers. I think we need more of that. So asphaltenes are our resource. So can we actually have value-added product as opposed to just selling our crude, right? Like, so you were talking about, and Alberta Innovates has done really extensive techno-economic analysis, and they see that there's a huge value if you can actually, if you can produce these strong carbon fibers that now is high value-added material. I think like you see more and more around, well, even from our university, there's cool research where we use CO2 as a building block to essentially now develop new nanomaterials. I will take an example of the company that spun out of my lab, so NVCore. NVCore does develop the technologies to essentially mitigate tailings problems and transform all these tailings in oil sands and hard rock sector into these thriving habitats. But at the same time, we're also looking at, can we extract valuables while we're actually mitigating this problem? Because there's a lot of valuable, and actually it happens to be nanoparticles that are super valuable, even in our own oil sands tailing sector, right? So essentially, like, we could be looking into how can we extract more of this from waste? How can we use our resources to develop something that is really unique? So I feel like these are just some of the areas where we can actually really play a role, and we already have shown leadership in comparison to the other countries.
Colin, do you want to add to that?
Sorry, it was...
Go ahead, Colin.
Sorry. Yeah, I would totally agree with Milana, and also, you know, there's a couple of spin-out companies already in Alberta that are extracting lithium from the brine water that's in tailing ponds, and the lithium is the major component that we need in batteries. And obviously, with all the move in the world towards, you know, not just portable electronics, which is more my kind of area, but also the batteries needed for electrical vehicles. Having more lithium is a massive import, because at the moment it's actually a bit of a limited resource around the world, and it's extracted through mining. So there's that side of it in terms of, you know, how, you know, moving forward into the future and the environment. But there's also within my own work, I do the brain machine interfaces. I make microelectrodes that interface with the brain. And there are, you know, the brain is actually one of the, you know, the biggest electronic circuits on the planet, and we don't really know how it works. We're only scratching the surface of that, and even, you know, Elon Musk has set up a company in this area to give an indication of how, you know, important this space is. To understand the differences that happen within our bodies, and, you know, mental health with COVID and everybody being online. Why do we get depressed, and how can we alleviate that? And there's a lot of studies there around deep brain stimulation, but also understanding why parts of our brains do the things they do, and how can we, stop people being potentially having addictions, for instance. So there's a big area there in terms of making smaller and smaller ways to interface with the brain. Some of that can be through kind of traditional fabrication processes, microfabrication coming from the silicon industry. But there's also the area of making these new nano-based materials, kind of like printable electronics in a respect. So kind of like your 3D printer, but for making electronics that you can then make into circuits and stuff like that. And also in the future, we all look at our computers, encryption and safety and data, more and more data is required. There's a lot of work being done at the quantum nano scale in how to increase the speed of communications. The Berkeley group in Faculty of Science here is doing a lot of research into the quantum nano world of quantum diamond and things like that. And this is all going to change how our communications work. Things will get faster and the better fibers for our communications around the planet. So nano is going to, not just in the biomedical field, but across many, many sectors, is going to impact the future of our society.
Oh, that's great. Thank you. We have a question from the audience. I'm going to ask Alex a question here. And Alex works in the area of climate adaptation for urban centers. And he's curious what Canada may be doing with respect to carbon nanotechnology and climate change mitigation. Would one of our panelists like to jump in on that question?
Well, maybe I can say something about carbon. So, I think Colin talked a little bit about that, and so did Milana. That one of the materials that is being studied a lot and talked about is graphene, and Canada is in a special position with respect to that, because we have these graphite deposits in Canada that are very high quality. And so it allows us to make these graphene materials that have, like we said at the beginning, these incredible properties in terms of for electronics and for other things, but also for batteries and electrodes and so on. And so when we think about climate change, at least the way I think about it is also how do we replace some of the things that we are using right now with more sustainable materials, technologies that will decrease our carbon footprint and so on. And I think that's the role of some of the nanomaterials that Canada is very good at developing and sourcing. There are many industries that have a large carbon footprint, but when we talk about Alberta, I just read about carbon black. So, from the oil and gas industry, there's been a transformation of carbon black to make chemicals much more efficiently. So the chemicals industry has quite a large footprint, and one of the promises of nanotechnology was maybe there's a way to make chemicals that doesn't use oil and gas, right? But you can use a byproduct of the oil and gas industry to get to that. So there, electrification, electrical cars, batteries, and so on. These are incredibly important technologies for mitigating the climate change that we're seeing now. So all of these things, and that's why we talked about advanced materials and nanotechnology. They go hand in hand. You have to really push the frontiers on all of these fronts to come up with some solutions. And we're at the point now where things are critical.
I'd like to give an example of it's a picture I use in one of my undergraduate courses of one of the first computers going back many, many years, and it had literally these things called valves that generated lots and lots of heat. And they took up an entire room, and our mobile phones are currently much more powerful than these now. So by miniaturizing things, we're reducing the power, we're reducing the amount of materials that we use, and we're also basically making things more efficient. And as we have more and more of these, these electronic devices, or as Marie said, the cars, we need to have the power come from somewhere. So we want to use it well. And one huge area where power is lost is the transmission of power on power lines. Basically, between where the power is generated at the power station, whatever it's sustainable wind power, solar power, or whether it's a nuclear reactor or it's coal-fired power plant or a dam, you have to use wires. And the wires have a resistance, and they can basically lose the power over time, lose power over the distance. If you make the wires superconductive at normal operating temperatures, then you have no loss of power. So that's another major impact on how nanotechnology can change things, because nanotechnology has led to superconducting materials, and some are now at room temperature. If we can change how the whole grid is working and becomes way more efficient, then we will have a massive impact on cities, and basically it will have a big impact on just how we use power.
And maybe I can just add to that. And I think, like, Marie and Colin already mentioned a lot of this, but I think, like, it's also interesting to think about that as that it has to really be what I would call, like, top down and bottom up approach kind of thing. So you have to have strategic mandates in place. We can develop the best technologies in the lab without the means to commercialize them. It becomes, they stay in the lab, right? So I think, like, there's, if you look at, and there's signs out there. Like, I mean, I think, like, we've seen the shift. Probably Colin and I'm assuming we joined UFC around the same time. And we've seen the shift in that. There is more push for commercialization, or enabling, really, the knowledge transfer from the universities. But then if you look at also the provincial side of things, like, you see more and more investment in the clean tech. And I can't remember, a month ago or something, like, I think, like, I read the news, there were around $50 million investment from the Alberta government into this clean energy sector. If you start thinking about clean energy sector, the odds are you will see the nanotechnology in there in some aspect, right? So I think, like, it has to really come from both ends. And I think, like, federal government, provincial government, I think we will be seeing more of that shift. We see more and more of those signs as essentially, like, investment has to happen for things to also occur and to start going and excelling. And while I truly believe that any nanotechnology we can capitalize and really, like, use nanotechnology advancements regardless where they are in the world, but it would be great if we can develop them in Canada, because that's, leads to the economic prosperity and everything else. But so that's my take on, like, how can we actually play a better role in this. So I think, like, we're starting to see positive signs of the investment from, and also, like, as I said, that top down and bottom up approach.
Just extending that a little bit from an Alberta context, and then maybe also from a Canadian context, but we definitely do want to hear about the Alberta context. Where do you see the nanotechnology industry in Alberta from where it is now? Where do you think it's going to be in the next 3 to 5 years? Are we going to go through a period of sort of large and rapid growth, or is it going to be, do you think it'll be more steady?
I'm going to jump on that one, because I was involved with the original previous Alberta government program called the Alberta Nano Strategy. And that came about in 2007, 2008. So the province put money into facilities like the Microsystems Hub and the Nanofab in Edmonton to stimulate the formation of companies to help researchers, because the equipment used is very expensive. So the government has been putting the money in. Alberta has been investing, as has other agencies around the world. So Maureen probably can talk more about the global impact. But if the government hadn't done that, we probably wouldn't be having this conversation, because the research wouldn't be happening, to be sure.
I think as well, it needs to be a patient investment. You know, I think, and Milena talked about the crystalline nanocellulose plant in Alberta. Well, you know, I've had some colleagues from the US saying, how did you do that? Like, how come Canada is ahead of us? Or, you know, you've had this pilot plant and now you have these other plants in Quebec. Um, you know, what gave rise? How did you get to that point, right? So it's a question of strategy, but it's also a question of patience, because you need to build the critical mass around these facilities and keep up with what's going on in the rest of the world. And that's the importance of being on the global market to see what's going on. So it's not sufficient to invest in a facility like that. You have to continue to invest and be patient and have enough people around it to develop the applications and so on. And I think, you know, we're seeing that play out in health. I think with the COVID vaccine, why is it that that we had this great idea for messenger RNA lipid nanoparticle, and yet it's being done in the rest of the world and not in Canada? Why can't we have our own vaccine? We don't have the manufacturing capacity here to do the clinical trial, the materials manufacturing for clinical trials. That's the gap, you know. So there needs to be a strategy to address that gap and make sure that there's that supply chain to make sure that we can do that in Canada, right? That we just don't give away, you know, our intellectual property to others to develop. So we need to stay at the forefront by addressing those critical gaps. And unfortunately, they're often expensive. It's an expensive step to take, but you know, it's you need to capitalize on all of the investment that you've done in research. So I think for me, the nanotechnology is really we're now seeing the really fantastic applications coming to bear, but we need to keep the eye on the ball in terms of the strategic investments to make sure that stays in Canada.
So I think we have time for one last question. And whenever there's something this new and it's something that we can't even see, one can imagine that there's a lot of myths going around. And so I wonder if each of you could speak to a nanotechnology myth and what's the reality of that. And if you don't got examples, I've got a few that I'd love to hear your reaction to. Alana, do you want to start?
Sure. So, well, I feel like, you know, there's many myths, but I feel like Marie mentioned already before, like health and safety aspect of it. So I think like I'll let her elaborate on that. I think one of the myths that we saw for a while is like it doesn't work. What's all the hype? You can actually, even if you Google graphene, you will see, for example, we talked about or carbon nanotubes and any of these, or MXenes, any of these two-dimensional materials, you will see probably gazillion of papers out there saying what's all the hype about? Is it really worth the money? Because we didn't see all of these promises that they were supposed to have, right? But I think, like, as I mentioned, I already touched on this before, you cannot essentially go nanoparticle without, like, you know, just producing the nanoparticle without also investigating how to structure it, how to assemble it in the best possible way for the application of interest. So I think if you attended Stephen Bryan's talk, he talked a lot about nanostructured complex fluids that will be that are really useful in the oil and gas applications, for example. But if you look at industry historically, it's not something that they were like, okay, yeah, they would never think about nanoparticle as actually being useful, or can it actually survive in the reservoir conditions, which is obviously, we know how deep and how complex these structures are, these geological formations are. So I feel like, you know, this myth, it doesn't work, is obviously something that, you know, it's on our shoulders to prove wrong. And I feel like we have already, like if you look at what's out there, so if you look at the airplanes, Boeing airplanes are already like, you know, have like a large components of carbon nanotubes because we need lighter airplanes to save on fuel. So if you want to think about carbon neutrality, if you want to think about like climate change, we have to think about like these also lighter materials, more insulated materials. We have more and more applications in concrete, but you know, or it's too expensive, or in order for me to make a nanoparticle, I will actually produce so much of CO2. Can I offset it when I actually input it and get this increased efficiency? So there's really several myths on just performance side of things. So I'll stop here and let the others take on other aspects of it.
Thank you. Why don't we go Colin and then Marie to finish things up?
Sure, I'll just come up with a very simple one that's kind of more not as in depth as Milana's. You know, the way nanotech is portrayed in the media and movies like, you know, Iron Man and things, where the suit just comes out of nothing and they just, you know, that is definitely a myth. But there is work being done.
I am
on,
so
I know, I'm
to hear
sorry.
the Iron Man suits.
Don't tell your kids, Bill. But you know, nanoparticles and nanorobots and swarms are real, and you can see online on YouTube and things swarms of drones, and the concepts behind that can be applied to nanorobotics as we move forward and miniaturize these things. But I'll just leave it at that. And let Marie have a comment. I think we're running out of time.
Thank you, Marie, and you get the last word for our panel.
I think that, you know, just to echo what Milana said, this business that, well, it doesn't work or nothing has come out of it. It's actually, it's in so many things as an enabling technology, it's affecting all sectors. And so if you're sitting in your car, there is nanotechnology in your car in different systems, from the foam in your car seat to you know, the electronics in your car. It's in aerospace. It's in everything. I said cosmetics. We just we're not aware of it, right? And it's not a surprise because the world was very scared by GMOs. And when nanotechnology came around in 2000, there was this, well, we don't want this to be like GMOs, right? So let's be careful about, and let's take the time to understand what's going on and how safe it is and so on. But it is an enabling technology, and it affects, you know, it can be used in all sorts of things, and that's playing out in personalized medicine now. And I think that's, for me, that's the most exciting thing that as I look in the future, I think, well, many of the things that where some of the disease we think are incurable now may not be and will be our personalized, you know, drugs for that disease. So I think the future looks very bright, and we have to think about it. We don't think about photonics. And yet it's in everything. It's in our TVs and so on. And it's exactly the same with nanotechnology.
Marie, Milana, Colin, thank you very much for your time and your thoughts in this panel here today. I really enjoyed it, and I know our participants, our audience also enjoyed it. And of course, thank you to the audience for joining us here today. This does wrap things up. We've had a really good hour diving into the world of nanotechnologies. And I'll close by just reminding everyone, on April 22nd, we will be hosting our Engineering, Biometrics, and Wearable Technologies Schulich Connects session. And I hope to see everyone there as well. Thank you all very much, and stay safe and have a great weekend.